Hello, everybody. Welcome. We are very excited to have you here to chat about Delta Live Tables. We have Michael Armbrust, the original creator of Spark SQL, structured streaming, and Delta, and he's going to take it away.
Thank you so much for coming. I am super excited to be here today to talk about what Matt just alluded to is almost 10 years in the making. Starting in 2013 with Spark SQL, and then structured streaming, and then Delta, we now have Delta Live Tables, a single declarative framework that brings all of these technologies together into a simple system that allows you to create and update the data sets in your lakehouse. So why do you need DLT? Let's start with the motivation. So, as I'm sure you all know, good data is the foundation of the lakehouse. And many people have bought into this bronze, silver, and gold architecture where you start with messy data and you incrementally clean it up until it's ready to be those business-level aggregates that actually drive your business and help you make decisions. But this picture is a lie. No data pipeline is this simple. They're often much more complicated with a bunch of different inputs and different intermediate tables. And this reality means that it gets increasingly complicated for you as an engineer to build these systems. What does it actually look like to do a day in the life as a data professional? So a pretty typical thing is the CEO will email you. There's some really important question that he needs an answer to. And all you have is a giant directory full of JSON files. And your goal here is to turn this into a beautiful dashboard that drives insights for the business. And I'm a little biased, but when I get something like this, I start with my two favorite tools, Spark SQL and Delta, and we write some queries. It's super easy to ingest this JSON data into a table, and then it's super easy to clean it up. And then I can build this dashboard so my CEO knows what to do next for the business. But then no good deed goes unpunished. And instead of just wanting the report one time, he wants a production pipeline that updates it every single day, or even worse, every single minute. What does it take to take these two SQL queries and turn them into a production pipeline? Well, first, you're going to have to figure out dependency management. There's multiple tables here that need to be updated in the right order. We need to handle failures and things. We're going to have to do it efficiently, so we're going to have to break it up into partitions and make it so that we only recompute individual days at a time rather than complete data sets. We're going to have to implement checkpointing and retries, because in the cloud, things always fail. We have to add quality checks, just in case bad data comes into the system. I don't want that confusing my downstream consumers. We need governance, because this is sensitive data and only the right people should have access to it. We need discovery, so the right people can find it and use it to make decisions. We need to handle backfills in case the requirements change. Version control, so I can work with my coworkers, and deployment infrastructure. And man, this is getting super complicated. What you realize is the time spent on tooling starts to dominate the complexity. And you're not focusing on the one thing that you should be focusing on, which is getting value from data. And this is the idea of DLT. Instead of focusing on all of that infrastructure, you write these declarative SQL queries, and we provide the infrastructure that takes care of all of these other concerns underneath the covers. Now, I've said this a couple of times, declarative programming. What do I mean when I say declarative programming? The key trick of a declarative program is it says what should be done, but it does not say how to do it. And here I have two examples. A super simple example where we want to add up a bunch of numbers. The imperative program actually has to have a for loop, and it has to iterate through the array. It has to add them up, and it has to print out the answer. It says exactly how to do it. A declarative program, on the other hand, just says, I want to know the sum of these numbers. And if you translate, and the idea here is the query optimizer figures out the best way to execute it. If there are statistics that allow me to calculate that sum more quickly, it can automatically go and use those statistics instead of reading the raw data. And another pretty cool trick here is you have data independence. So as the underlying physical data changes, the query optimizer can decide what is now the best strategy to do it. And if we translate this into Spark, it's very similar. If you think about your average Spark program, an imperative Spark program will tell you exactly what needs to be done. It will say things like, overwrite this partition. Whereas a declarative DLT program is just going to say, this table should exist, and it should have this answer stored inside of it. And then it is the DLT runtime's job to figure out what is the best way to create or update this table. Now, a very common question that I want to make sure I answer before we get too deep into this is, should I be using Databricks workflows, or should I be using DLT? And pretty much very commonly, the answer is both. Workflows is used to orchestrate anything, including DLT. So if you want to run your DLT pipeline at some schedule, or when some other tasks have completed, or when a file arrives in the cloud, or soon when another table is updated inside of Unity Catalog, these are all things you would use workflows to orchestrate. And then DLT is one of those task types. It's closer to DBR than it is to workflows. And that's what it does is it creates or updates Delta tables, and it runs structured streaming. So it's specifically about data flow. Now, why do we want to use declarative programming? Well, the key idea here is if we understand your objective rather than a set of instructions about what to do, we can take care of all the boring stuff for you. So you can eliminate a lot of boilerplate in your data pipelines. You don't have to worry about fault tolerance. You don't have to worry about state management where your checkpoints are stored. You don't have to worry about object lifecycle, like creating or deleting tables. You don't have to worry about scheduling all of the dependencies in your pipeline between all of the different tables. And you don't have to solve a bunch of common data problems that are undifferentiated heavy lifting for your business, doing change data capture, evolving the schema of tables. Everybody has to do this, and we've created one system that can do it for you. The other really cool trick is we can dynamically optimize based on the current status of the system or even across multiple queries in the system. And it also allows us to do better operations. I want to tell you about a really cool trick that we've developed in the last year called HMR, or health-mediated releases. I'm sure all of you, don't like having to upgrade your DBR versions. It's always really scary to see what's changed, what behavior changes have happened, how is that going to break your pipelines. HMR makes this our problem. So what we do is we automatically upgrade your pipelines under the covers. And if we ever detect that after an upgrade, a pipeline is failing, we will roll it back to the previous version automatically using our retries. All of our code is idempotent so that we know that this is safe. And if it works on the old version, we now have a very strong signal that there's a bug in DBR. We'll open a ticket on our side, we'll pin your pipeline to the old version, and it will keep running. And you have no idea that there's been a problem. Meanwhile, Databricks engineers are busy fixing that bug, and eventually we'll roll you forward. In some cases, we haven't even been able to contact customers to tell them their pipeline was broken, because it just kept working and they never noticed. So these are all the things that are enabled when you program declaratively instead of imperatively. Now, DLT has two core abstractions, and I'm going to be talking about these for the next 90 minutes. The two core abstractions are two different types of data sets. You define these, and DLT keeps them up to date. The first abstraction is called a streaming table. A streaming table is a delta table, and it behaves just like a delta table in many ways. And the only difference is it has a stream writing to it. And I'll talk about what you use that for, but in general, use it for ingestion, use it for low latency transformations, and use it for processing huge amounts of data where you can never afford to do recomputation. And on the other side, we have materialized views. Materialized views are different. They're not a table. You can't write to them. They are the results of a query that has been pre-computed. We do store it in Delta, but your mental model here should just be that it is the answer to a query. So you write a SQL query, we materialize it. These are very powerful, and you can use them for transforming data, building up aggregate reports, and also speeding up BI queries in your dashboards. So let's deep dive into streaming tables here. I'm showing the syntax, so it should look very familiar to anybody who knows SQL. You say create streaming table, you give it a name, and then you write a SQL query. And in this case, I'm reading from the Cloud Files data source, which is the system we have called Autoloader. It can ingest any collection of files from any cloud storage system, guaranteeing exactly once, picking up exactly where it left off. So it basically gives you this read-only data set. And it'll, even if as you add more data, it will only read that new data that has just arrived. And the reason that's so important is because it allows you to reduce cost and latency by not repeating the same work over and over and over again. And like I said before, this is a table. So in addition to the stream writing to it, you can do DML on it. So if you want to run update, delete, merge, it's a table. You can do all of those operations on it just like a normal table in Unity Catalog. The other abstraction here is a materialized view. Here's an example. So here I'm creating a report that tells us how much profit we made each day, and it computes it. And the guarantee here is anytime you query a materialized view, it will return the results of that query as a snapshot at the last time that materialized view was updated. So you can schedule it to refresh, and it will always contain exactly the answer to that query. You cannot modify the data in it. You cannot insert, update, or delete it. If you want to change the contents of a materialized view, you change the query definition. So if you want to remove a row from it, you add a filter to filter that row out. One really cool trick of DLT is this thing called expectations. All pipelines need to have data quality controls, because even if you know that all of your logic is correct, you're not controlling what happens upstream from you. And it's very common for someone to change a column name, change a data type, and have that break your pipelines. And if you don't have quality controls in place, you won't even know that that's happening. Expectations are basically these single Boolean expressions that are evaluated on every row. And they're very similar to constraints in a traditional relational database. But the reason they're more powerful than constraints, which can only fail when they see something unexpected, is because they have flexible policies that allow you to choose exactly what should happen when your expectations are violated. You can choose to just track how many bad records there are, and we'll show you that in the UI as a percentage. And you can say, I'm not worried as long as less than 5% of the data is bad. You can drop records so they don't affect downstream processing, but this is much better than just putting a filter in your query, because the filter is not going to tell you if it accidentally starts filtering out 90% of the input data. And then if it is some super important gold table that you're going to report to regulators, and you really never want bad data to get into it, you can choose to abort processing as soon as the expectation is violated, roll that transaction back. And we have an extra cool trick here. We actually add lineage. We rewrite the Spark query plan to track which row in the input caused the bad row in the output, and we'll show you that. So it makes it much easier to debug where this bad data was coming from. Expectations might sound really simple. You might say, well, if I can only write a Boolean expression over a single row, how can I do powerful data quality constraints with that? Well, let me give a couple of examples, because once you start combining it with materialized views, you could start doing some pretty cool stuff. Let's say I want to, for example, enforce a primary key constraint. I want to make sure that this value is unique within a table. Well, that's pretty simple. I just create a materialized view. I count how many occurrences there are of each key, and I have an expectation that there is exactly one. And this will not only tell me if that primary key constraint is violated, it'll make it very easy for me to figure out which key is violating it. And as I'll show you, there's actually some pretty cute ways that we can keep this materialized view up to date incrementally. Another example here is joins. It's very common when you're joining against some dimension table, and your foreign key constraint might be violated. A pretty common problem you have in data pipelines is those rows will just be dropped silently, and you'll never know that they were being dropped. Well, a cool trick you can do with expectations is you just translate that into an outer join. You don't want those bad rows to make it downstream, so you put an expectation on it. And you say, I'm going to expect that the other side of the join is there, and now any missing records will show up as bad data inside of your UI when you look at your pipeline. Cool. So I want to make my first announcement of the talk. Up until now, when you wanted to use DLT, you had to go into the workspace, you had to create a pipeline, you had to create a notebook. There was all of this overhead. And that's why I'm really excited to announce that we're releasing DLT in DB-SQL. You now have the full power of streaming tables and materialized views in DB-SQL. And so this one line of code here is actually creating a robust, scalable, incremental ingestion pipeline with just this one SQL DML command. And people who have been using DLT might be saying, Michael, where did live tables go? Where did streaming live tables go? They didn't go anywhere. We're just unifying the terminology so that we use the same words across the entire Databricks product. A streaming live table is a streaming table. A live table is a materialized view. They have the exact same semantics. We will continue to support the old syntax forever, but we want to have one simple way to talk about this stuff across the entire lakehouse. Cool. And with that, I would like to bring up Franco, who's going to demonstrate creating MVs and STs with DB-SQL, and with a bonus, DBT as well.
Thanks, everybody. Thank you. Hopefully everyone's having a great summit. All right. So thank you, Michael, for that awesome introduction. If you all don't know me, my name is Franco Patano. I lead up the data warehousing and BI practice at Databricks SQL, predominantly Databricks, our Databricks SQL product. One thing that I have been longing for, and a lot of customers that I talk to have been asking for, you have streaming in Databricks. Why can't I stream a table from Databricks SQL or in your SQL API? Why do my data warehousing people have to learn just a little PySpark or Python to be able to leverage your streaming capabilities? And I was like, yeah, why not? And Michael and Paul came up to me, and they asked me before this, hey, how would you like to talk about streaming tables and materialized views in DB SQL? It's like, I'd love to. People ask about this all the time. So it is my absolute pleasure to show you all streaming tables and materialized views in our Databricks SQL product. So let's take a journey together. First off, I am a data warehousing professional. I work at an organization where we have these wearable devices. You can, they track your calories, steps, and stuff like that. And we also have the device data, and we have the user data. And my company just asked me, the data warehousing person, hey, I get this JSON data and the CSV data. We need you to create pipelines and ingest them, and we need to be able to put them in our BI reports. Great. Can I do this in SQL? Let's do it together. So first off, there's this brand new function that we have called read files. This is absolutely amazing. Read files is autoloader under the covers. It will infer the schema of the data, and it will also understand that the first row is a header, and it will infer that schema. And it will essentially display the results for you, where then I can see exactly what's going on in this table. Fun times. All right. So essentially, it will show me the results of the table, and then I can go ahead and create my streaming table syntax. And from there, you can see here that this is the new streaming table syntax that we have. Essentially, you can create streaming table like Michael had earlier, and you would define the table schema, and then you would say as select. And I always like to cast my types. Implicit type conversion isn't always great. You want to be explicit, especially when you're making durable pipelines. And now I create that streaming table. Awesome. So I go back over here. This is what the data looks like after the query completes. So I can go ahead and browse that data through refiles, and I understand it. Now, I also have the same files that I'm getting on my user data, except these are CSVs. So I did the same thing. I did a read files on those CSVs, and within the same SQL browser, in the same SQL experience, I was able to build the user table as well. So now I'm ingesting both of these tables as streaming tables. But my job's not done yet. My business asks, we need to join these two data sets together, because we need to understand what the users are doing, like how are they interacting with these devices, what are the results. And so in my user table, I have their risk factor, so that they created a feature called risk or a column called risk that had different capabilities, like what risk these people are, as well as their age. And I wanted to understand, the business wanted to understand what are the average calories burnt, how many records we're receiving, so are we actually getting the records all the time off these devices, and then what were the average number of steps and miles walked. And from here, I essentially can look at my aggregates of how I would want to browse this. One special thing that not a lot of people know about that I want you all to know about is group by all. Group by all is amazing for when you have aggregates, because essentially what it does is it tells the optimizer, hey, or the planner, hey, all of my non-aggregate columns in my query, group by those. So you don't have to say group by 1, 2, 3, or group by your columns. You just say group by all, and it will tell the interpreter, boom, just group by all my non-aggregate columns. And that's awesome. Thanks, Reynold, for this, if you're out there. He actually made the commit. And then what I want to do is I want to take that aggregate I just created, and I want to create my materialized view. So I'm going to take that SQL statement that I created, and I'm going to create a new materialized view. And then you want to enable change data feed, because that's some of the capabilities behind materialized views. And I'm going to take that SQL statement, I'm going to pop that in there, and now I can create a materialized view. Excellent. So I essentially just, in the past 2 minutes, I was able to, as a SQL user, I never left the SQL API. I ingested JSON data off of Object Store. I ingested CSV data. I created an aggregate, and then I created a materialized view. This is great. But here at this organization, we are a DBT shop. So I'm going to put my DBT hat on, and we are going to flip over to VS Code. To anyone who wants to use DBT Cloud, you will be able to do that there too. It's just we had to use a custom version, a custom build, so we had to do this locally. But essentially, I'm going to take my DBT starter project here. I created my users table. I just brought that SQL statement in with DBT. I just need to say config materialized equals streaming table. The beautiful part here is that DLT handles the incremental ingestion off object store. You don't have to, as DBT users, we don't have to do the Rube Goldberg machine of figuring out how to do incrementalization. Streaming tables just handles all that for us. This is amazing. And the other thing that people don't realize is you can do this over the wire, over any of our protocols. So if you use JDBC, ODBC, or use our REST API, or use Node, Go, the execution, anything, you can now create streaming tables virtually from any application. So any partners out there, you can build streaming tables as well. And I'm going to do the same thing for devices. I'm going to call it my streaming table, materialize, and then I'm going to bring my SQL code that I used in the browser. And finally, I'm going to create that materialized view. And again, the config for materialized is materialized view. And then the table property, I want to turn on that change data feed, and I'm going to bring that SQL statement in here. Awesome. And then what I'm going to do is I'm going to go into Databricks jobs, and I kind of already did this beforehand, but I'll just show you how it works. Essentially, I committed this to get my GitHub repo. I told the Databricks job, go grab that repo, run it on a Databricks SQL warehouse. And it did that. So now, awesome. My DBT code is checked in. I have my version control. I ran my job. Let's check out my tables. And so from here, you can see we have that DBT database that has all our tables in it. So we go into users. We're able to browse users. I don't know if you all noticed this, but one of the awesome things I love about the Data Explorer, do you all notice the icon for the streaming tables and materialized view? That is really cool. So you can tell exactly in the UI, is this a streaming table or materialized view? Your users can actually tell what they are. And here, you can see the two tables that I ingested. We can browse some of their sample data. I want to look at some of that sample data for that user activity, materialized view I created. Everything is great. I want to show this. Change this to the warehouse. I might get an error on this next one if I don't. And then in details, you can even see information about this query. So it'll show you the SQL query. It'll tell you it's a materialized view, and it'll give you all the information that you need to know about this. So now, as a data warehousing user, this is amazing. I get incrementalization using streaming tables that's super simple. I get materialized views, and now it all works from DBT. So you don't have to decide, is it DBT or DLT? There is no decision. Use them both. It's great. And with that, I'll give it back to Michael. Thank you.
That was awesome. Very cool. Anybody who knows even just a little bit of SQL is a full-fledged data engineer. Cool. So now that we understand the basic concepts and we know how to create streaming tables and materialized views, I want to do a deep dive into structured streaming and how it works inside of DLT. So as I just hinted to, all of structured streaming is available inside of DLT. It's based on exactly the same engine. We're just a really good way to run structured streaming. The streaming computation model is pretty simple. The basic idea is the input is an append-only table. And you might say, well, I don't have many of those. But it turns out there's many things that actually fit into this model. Files getting uploaded to cloud storage can be modeled in this way. Message buses like Kafka, Kinesis, or Event Hub. Delta tables where you're only appending to them. Transaction logs of other databases are all examples of append-only tables. And the magic trick of structured streaming is rather than wait for all of the data to arrive and then run a Spark SQL query over it, structured streaming allows you to produce results on demand as new data arrives. And we incrementally keep those results up to date. And the reason this is great is because you get much lower latency when you're only processing one new record, and you get significantly reduced costs when you're avoiding all of that redundant work. And a key thing that I want to make sure everyone understands, because often I hear people when I talk about this, they say, you know what, I can't afford streaming. I don't care about latency. That's too expensive for me. And that is not how structured streaming works. Structured streaming is often cheaper than running a batch job. And the magic trick here is you can run structured streaming in several different ways. you can run it manually, only when you want this table to be updated. You can use Databricks workflows to schedule it. So you can say, I want this to be updated once an hour, once a day, once a week, once a month, whatever works for your business. Or if you do have low latency requirements, we can support that. And then you put the pipeline into what we call continuous mode. In this case, a cluster is always kept running, and we're just constantly polling for new data and updating the answer as soon as new data has arrived. And the really cool thing about this is, as you move between this spectrum of cost versus latency, there are no changes to your code. So you can build your pipeline once, and if the business requirements change, all you have to do is change the schedule. And kind of automatically, you spend a little bit more money, and you get fresher results. Now, a key thing, and like pretty much every single time you're doing ingestion, you should be asking yourself, should I be using a streaming table? It's kind of a no-brainer. You never want to ingest the same data over and over again. And so, as we've been showing, we have this pretty cool UDF or table-valued function called cloud files. What it does under the covers is it uses RocksDB, and it remembers exactly which files have been ingested. And then it transactionally communicates this information to Delta using our transaction identifiers to guarantee that even in the presence of failures and restarts, we will ingest each row of each file exactly once. It works with all the cloud storage systems, and it supports arbitrary scale. The problem is this. If you have a directory with 10 million files in it, even just listing those 10 million files to figure out which one is new takes a really long time. And so what Autoloader does is it integrates with the notification systems of all 3 major clouds so that they will tell us when new files arrive, and we don't have to scan all 10 million files each time. This lets us handle just massive, massive scale. And then finally, it does schema inference and evolution. So it will figure out what the schema of those data sets are, and if new columns appear, you can set policies on how to handle them. You can say, anytime something changes, let me know, throw an error. Or you can say, just automatically add those columns to the table. It depends on your use case, what the best thing to do is. And it supports all the different data formats, JSON, CSV, text files. We're adding support for XML. So it's a pretty cool tool for ingesting data. Another really common use case is ingesting data from message buses like Kafka. And you can see here I've switched to Python syntax. So I haven't talked about this too much, but everything I've been talking about so far can also be done in Python. And you can see it's pretty simple. You just have a function that's annotated as a DLT table, and it returns a data frame. This is just like the as-select part of the SQL queries that we've been showing so far. The Kafka source, very similar to Autoloader, automatically tracks what data has already been ingested. It keeps track of those partitions and offsets and makes sure that we ingest that Kafka data exactly once. And you can use any structured streaming source that's included in the Databricks runtime in this way. And this is often what you want to do when you need the lowest latency ingestion. Because uploading files is big and chunky. You want to wait until you have enough data for a file. Message buses are a very efficient way to ingest small numbers of records at a time. Or if you have IoT use cases where many people are sending those records, a message bus acts as a nice buffer. It collects them so you can make nice big commits to the Delta table and just have more efficient computation there. You can also stream from any Delta table. So in this example, I'm using the stream function. And you can see I can read from tables that are in the catalog. That's the first example where I say from stream prod.events. Or I can just read from random Delta tables that are stored out in cloud storage. So in this case, I use the other syntax where I use the virtual Delta schema, and I just give a path to the table. This only works for append-only Delta tables, though. And I'll talk about that in a little bit. But as we said before, the computation model of structured streaming is an append-only stream. It does not understand how to handle changes, and I'll go into some of those details in a bit. So one of the key things when you use streaming is state. I keep talking about this. I keep talking about exactly once. It remembers what rows have been ingested. And this is the key thing you need to understand when you're using streaming. Let me give you a couple of examples of how state can change the results in your queries. So each row is processed only once. If you remember only one thing about streaming from this talk, this is kind of the key detail. One consequence of this is if I change the definition of a streaming table, so I change that query there, for example, instead of being a plus 1, I change it to a times 2, we do not go back in time and recompute all of those old results. And this is critical when you have huge tables. You cannot afford to recompute all of the data that's been computed in the past just because you wanted to add a column or fix a bug or do something. And so when new data comes in, it will use the new definition, but that old data is going to remain unchanged. Another example where state matters is with streaming joins. So when you join a stream against a static delta table, what you're going to do is you're always going to be joining with an up-to-date snapshot of that table. So every single microbatch, we're going to update that other delta table and take the latest results that are there. But if that table changes, again, we don't go back in time and update records that have already been joined with. Those stay the same. So in this example, I'm joining with this cities table, and you can see I'm joining with Berkeley, and it's misspelled. And let's say I go and update it to fix the spelling and make it correct. Only this new record that came in after the change was made is going to have the new join value. Now, you might say, well, what happens if I do want to update all of that data? There was a critical mistake, and I need to update my pipelines. Well, we make that easy. Backfill is a built-in feature inside of DLT. We can automatically perform this through what is called a full refresh. So let's go back to that original example. I changed the streaming query here, and I now have this table that is in this heterogeneous state. I want to make it all use that new query. I'm either going to run the SQL command, refresh table full, or in the UI, just click this button, full refresh. And there's also a REST API to do this. And it will then recompute the entire table from scratch. And this only works if your streaming source has full retention. So a good best practice here is always put your data into Delta. Because Kafka, you can store a couple of weeks of data, similar with Kinesis. Delta, you can store as much data as you can afford for as long as you want. And when you start a stream from a Delta table, it always starts with a full snapshot of that table at the moment that you started the stream. And so it makes it very easy to do these full refresh cases when you want to do it. Stream joins. This is, I would say, one of the least understood features of structured streaming. I regularly see users trying to use stream joins for things that they cannot do. So let's talk about what stream joins are actually for. A stream join is for when you have co-arriving facts with a bound between how long apart their arrival can be. The canonical example is ad tech. You're Google, and you have impressions, and you have clicks. Two different systems are producing these data sets, but they happen very close to each other because users always click on the ads right away. They don't come back to the page 10 days later. And so the magic trick here is you have these two streams. They both have watermarks on them. You have a join condition, and you have this time bound. If these things are not true and you use a stream join, it's going to buffer all of the data forever. So you cannot use this for updating dimension tables or cases where you don't have a bound between their arrival. But if you do have a bound between their arrival, this is a very powerful feature. But I wanted to make sure to clarify what it should be used for. It is not all types of joins in all cases. And I will talk about how to solve those in a moment. A really cool trick that we just added to DLT is the ability to evolve your streaming sources, to add and remove them over time. And first I want to kind of start with the mental model. What's actually happening under the covers when you create a streaming table? So let's start with this simple syntax, create streaming table raw data from Kafka. What's actually happening under the covers is this is syntactic sugar. It's creating two different objects under the covers. There is a streaming table, and there is this flow with the same name that is actually reading from Kafka and inserting that data into the table. And the name of that flow is how the checkpoints work. So raw data is the name of the flow. There is a checkpoint called raw data. That is what is keeping track of the Kafka topic. And now you can see why there might be a problem if you start changing your streaming sources over time. If I switch this from reading from this Kafka instance to reading from autoloader, or from reading to a different Kafka instance that has totally different offsets, it's not going to make any sense. You have to use a different stream if you're going to be reading from a different source. And this is where multi-flow tables come into play. This allows you to evolve your streaming sources by giving each of those flows different names and different state. So in this example, I've created 3 different flows. One reading from my East instance of Kafka, one reading from my West instance of Kafka, and another one reading from the European instance of Kafka. And you can add and remove these over time, and DLT will keep track of exactly which checkpoints should be used for which flows. And this is really cool, because now you can add and remove sources without having to do a full refresh. And that is coming soon. Another really cool trick with streaming is change data capture. The problem is as follows. You have an operational database, and you want to get that database into your lakehouse so you can do analytics on it. And you don't want to dump an entire snapshot of that database every single time. That's really inefficient. But fortunately, most databases have this pretty cool trick. They can give you a feed of updates, deletes, and inserts that have happened, and you can then take that feed of changes and apply it into a Delta table. Many people today do this with for each batch and merge. And that's a totally reasonable way to do it. But also, many people today do this wrong. I actually made them delete a whole bunch of broken examples from the Databricks docs, because this is really hard to do correctly. And the reason is data does not always arrive in the correct order. And I'll talk about how we solve that problem in DLT in a little bit. But first, let's talk about the simple declarative way to do change data capture. So we have this new command called apply changes into, and let's break it down. Apply changes into has a source where we are reading these updates from. So in this case, I'm reading from another Delta table called city updates. And so it's going to create this table called cities where the updates are applied to. You have to tell it what the primary key is. This is how we identify each record. So when a new record comes in, we will look up the record with that key. If it doesn't exist, we will create it. If it does exist, we will update it. And then the magic comes in with this sequence number. So you say sequence by, and you give us some column. This can be any sequencing in your data set. It can be a timestamp. It can be a log sequence number. It can be the upload time, whatever makes sense in your application. But this is how we're going to decide what came first and what came after. And the guarantee here is that DLT will produce the correct answer as though the data arrived in the correct order, even if it doesn't. And so, in this example, a new record is going to come in, and we're going to update it, and the sequence number is greater, so everything works. And you can do CDC with DLT from any data source. So there's a wide variety of systems that can produce these change feeds, and you can read them from any streaming source. So you can read it from S3. You can read it directly from Debezium into Kafka. You can read it directly. We have customers that take Oracle Golden Gate, push it to Kinesis, and then read that data from Kinesis. This is kind of the cool thing about DLT is because it's just structured streaming under the covers, you can use all of those same building blocks when you're doing something like apply changes into. And a really cool trick, this is also coming soon, I just wanted to give a quick preview, is federated CDC with UC. Today, it's often a big struggle to get that change feed. How do I authenticate with Postgres? How do I configure it so that it gives me the right change feed? There are tools to do this, and you can run them on your own. I mentioned Debezium already, but it's often a whole bunch of work. And so, I think at Summit, we just announced query federation. You can now federate your Unity catalog with these other data sources. All of the tables from your Postgres or your MySQL instance will just show up there in Unity catalog. And what we're going to do is we're going to make the table changes function work with those federated data sources. So now all you need to do is say apply changes from table changes of that database, and we'll automatically handle all of the governance, getting the right permissions, and bringing that data into your lakehouse. Now I want to kind of dive under the covers and talk about some of the secrets about how we actually make all of this stuff work. Because handling out-of-order data is not trivial. And the trick that we use to do it is called reconciliation. Reconciliation allows us to hide all of the extra bookkeeping we have to do under the covers so that you get the right answer even though we're doing all this extra machinery underneath. So let's start with an example. Let's say I have a CDC feed, arrival time working downwards, and we have two operations that are updating on the same key. Now, what you'll notice here is, based on the timestamp, the delete should happen after the update. But actually, it arrived before the update because the update arrived late. And so if you were to just naively do a for each batch merge, what would happen here is you would have a permanent zombie row. That update would cause the row to be reborn, even though it's supposed to be gone, and it would live there forever, confusing all of your downstream users. So what we do in DLT is we have this magic trick where inside of Unity Catalog, we actually create what we call a backing table. This is the Delta table that has the actual information in it, and then this layer on top called the reconciliation view. That backing table has extra columns and extra rows. Those extra columns remember what version that row was last updated in. And if you're using some of our more advanced modes where you're actually accepting partial updates where only columns that have changed are included in the record. You actually have to do something a little bit more complicated. You actually have to keep a vector clock of every column and when it was updated. We keep all of this in extra columns within that table. We keep those tombstones to remember when a row was deleted so that we don't have a zombie. And then what the reconciliation view does is when you query that streaming table through Unity Catalog, it just filters all of this stuff out. And you see only the active rows exactly as you would expect. And of course, you can do DML on these things. So you can run update, delete, and merge. That goes through the reconciliation view. And if you absolutely have to, like for example, if some PII made it into one of our secret columns, you could modify them using this DML. Now, everything I just talked about is how it works in Unity Catalog. If you're using HMS, obviously we could not create a new streaming table object inside of HMS, and so we just create a view. So a question I get very often is, why, when I use apply changes into, is it creating a view instead of a table? It's because we have to do reconciliation in order to give you the correct answer. Another really cool trick with CDC is it's not only about keeping that up-to-date snapshot of what happens at exactly this moment, you can also use it to keep history. This is often called slowly changing dimensions type 1 or type 2. Type 1 is updating in place. Type 2 is keeping a history of every single change. And normally, this is even more complicated to implement. I found many examples of this being done incorrectly in our docs. And all you have to do with DLT is add this one extra clause to the bottom, stored as SCD type 2. And now when we get a change, what we're going to do instead, so let's say we change it to Berkeley and a new row appears, you'll notice there are these two extra columns, starts at and ends at, which tells you what time period was this version of this record valid for. And those timestamps are just your sequencing. So they are whatever number makes sense in your particular application. This is not something we make up. It's your timestamp, your log sequence number, however you are ordering the rows. And this is really cool. People sometimes use delta time travel for this, and that's great if you want to look back a couple days, maybe a week. But using delta time travel to keep years of history is a fundamentally inefficient way to do this. And you might say, why is that? Well, the reason is time travel thinks about physical files. And let's say you have a bunch of tiny files and you run optimize, and now it creates these big beefy files. Time travel doesn't know the data is the same. It's going to have to keep both the small files and the big files around forever. So you have a storage explosion when you try to keep history for a very long time using delta time travel. The magic trick of SCD type 2 is this is all inside of the delta table. We're only keeping rows that change, so you do not have the same storage explosion. So to summarize, you can keep history using SCD type 2. If you only want to keep a couple of days, you can use delta time travel. If you need to keep years, this is usually the right approach. Now, to get to some of the more complicated streaming concepts, chaining streaming. So having multiple hops of streaming where you use delta as an intermediate. And this works because delta is both a streaming source and a streaming sink. This is actually one of the kind of biggest things that helped delta take off in the early days. And so in this example, I'm reading a bunch of data into bronze from cloud files, and then I'm doing some extra augmentation in my silver table. This is a best practice. You don't want to do transformations in bronze, because if there's a mistake in your transformation and you've thrown away the raw data, you can never recover it. So keep your raw data exactly as is, and then transform it in a separate step. So if there's a bug in that transformation, you can always recover. And this is great. This is a great pattern when you have very large data or very low latency targets. But there's a gotcha. And it's this thing that I've kind of said several times. Again, this is one of the things that confuses people the most. You cannot do updates in streaming. Streaming assumes that everything is append only. So if you do this chaining streaming pattern, and you have updates, deletes, if you have apply changes writing into that table, which is also doing updates, if you have a query with a group by that doesn't have a watermark, it's computing an aggregation, and it's going to be updating the values of those aggregates. All of these things represent changes in a delta table. And what structured streaming is going to do when it sees those changes is it's going to say, I don't know how to process these. It's going to throw an exception. And so, there is a way to handle this. We just added this pretty cool feature where you can manually handle these updates, and it's called skip change commits. So basically what you're going to say is, don't worry about it, structured streaming. I've got it. Ignore those changes. I will propagate them manually. So streaming will do what it does best. It will propagate those appends down. And this is like a GDPR example. I have to delete from my bronze, and I also have to delete from my silver when I'm using this option. So this is great, again, when you have massive tables and you can never afford to recompute. You want to guarantee every row is only read once, and you're willing to deal with this extra complexity as a result. This is a great pattern to do. But this is getting pretty complicated. There's got to be a better way where I don't have to think about all this extra state. And that's why I am super excited about materialized views. Materialized views simplify transforming data. And as we said before, a materialized view guarantees it always returns the same results as the streaming query. There's nothing for you to reason about. You don't have to think about what it was in the past, or how it's changed, or what the watermark is. It is exactly the answer of that query. Compared to streaming tables, materialized views can handle updates, deletes, and appends in their inputs. They can support any window function or aggregation that you can do in Spark SQL. Joins work exactly the same. There's no stream, batch. There's just standard inner and outer joins. And they automatically handle changes to the query definition. If you change the materialized view, the next time you run it, you will get that updated answer. But there's a reason why we can have all of this power in materialized views. It's because unlike streaming, materialized views are allowed to read the input more than once. Consider the case where you're computing a max. The current value of that max is 10. Somebody tells you the record 10 is deleted. What's the new max? The only way to do that is to go back and look at the data and see what it is now. You can keep extra data structures and things, but you have to keep an arbitrary amount of state in order to compute this. And this is why materialized views are so much more powerful, because they can do what they need to do in order to compute the correct answer. Now, of course, recomputing from scratch every single time would be prohibitively expensive. Nobody would use materialized views if you always had to recompute the entire table. And that's why we built Enzyme. The idea of Enzyme is, instead of doing this one row is updated, replace the entire table, which is correct. It's trivially correct, which is why it's kind of a nice way to do it. We're going to do something a little bit smarter. We're going to notice only one row is updated, and we're only going to update that one row. And we have several techniques we use to accomplish this. So one technique is very similar to streaming. We leverage what's called a monotonic query, which is a query that does not lose any tuples given new input. So we know that appends will only lead to appends. We'll just feed those appends right through. Super efficient, as efficient as structured streaming. Only works for simple monotonic queries, though. Select, projects, inner joins. Does not handle changes to the input. So we have another strategy. Partition recompute. Every data engine in the room has actually built this by hand. DLT automates it. If you have two tables that are both partitioned in the same way, for example, by date, when a date changes, we will only recompute the date in the next table that has changed, rather than recomputing the whole table. And we do this very efficiently by just looking at the delta metadata to ask which partitions have changed. This is great, because now we can do aggregations. We can handle updates and deletes in our input. But it requires that these tables have the same partitioning, and that's not always true. Either you don't control it, or that partitioning doesn't make sense, like you should never partition by customer ID. And so we have a third technique, which is merging. This is basically using the last 50 to 60 years of database research. And the idea here is we basically compute what is the derivative of the query. We say, how is the output going to change when the input changes? And then we feed it through this new query that we've rewritten using Catalyst, and we figure out if these two changes happen, this row should change by 17, and we merge that into the final result. So this is the most powerful. We can handle arbitrarily complicated queries, and I'll talk a little bit about what we can do here. It can handle updates, deletes, and inserts. But merge is expensive, so this is not always the best thing to do. This is only a good idea if a tiny fraction of the table is changing. If the whole table is changing, well, it was cheaper to just recompute anyway. And it's pretty complicated to reason about. It is very hard to hand code this, but fortunately, we have some pretty awesome database engineers, including a professor who has been studying materialized views for many years, working on Enzyme. So how does Enzyme know which one to do? It's got all three of these options. Well, basically, we're building on top of Spark and Catalyst. We add into it the delta changes, so we can read the transaction log and see how the inputs are changing over time. And then we have a cost model, and we pick the optimal update strategy based on that cost model. A pretty cool trick that's happening under the covers is this thing called decomposition. Sometimes a SQL query as it's written isn't possible to incrementalize. How do you incrementalize something like count distinct? Well, the answer is you break it up into a simpler query. Instead of keeping just that, for every distinct aggregate, we'll create another table under the covers, and there we'll calculate the count grouped by the thing we're doing a distinct on. And now the number of rows in this materialization that we've created is the answer to that count distinct query. And we can answer it very efficiently because you can answer a count query over delta just by looking at statistics. So this allows us to incrementally pre-compute the answer to that distinct query by keeping a little extra information around. And so we're going to use a very similar trick to what we do with streaming tables, where inside of Unity Catalog, your materialized view is not necessarily even just one delta table. It might be many delta tables where we've broken your complicated query down into these simpler queries. And then there's a reconciliation view that says how to take these intermediate results and return the final answer. And very similarly, you query the materialized view, and you get the correct answer. And now I'd like to make my second announcement. We're releasing at the summit into public preview and private preview DLT serverless. And the really cool thing about DLT serverless is it has Enzyme enabled by default. So any materialized view that you create in DB-SQL will automatically use Enzyme, and any MV in a DLT pipeline running with serverless turned on will also use it. We're coming out the gate with 3 different techniques. We'll support these co-partitioned use cases, we'll support associative aggregation, and we'll support these monotonic queries. And we have a pretty awesome roadmap. And I would love to hear from people, what queries are you writing that are not incrementalizing today? We will use that to drive our roadmap so we can improve the incrementalization engine over time. I'll be super honest with you. I think Enzyme is like a 3 or 4 year project, but I'm really excited about what we can do with it. So this might sound too good to be true, so I would like to bring Nitin up, who's going to show us how it actually works.
Thank you, Michael, for the great introduction to Enzyme. Let me switch gears. OK. So, hi, everyone. My name is Nitin Sharma. I am an engineer at Databricks working in Delta Life team. For this demo, I'm going to assume the role of a data engineer who works in an e-commerce company, let's say. My team is responsible for creating orders-related data sets. And these data sets then can be used for analyzing orders, finding out daily trends and stuff like that. For that, I built this pipeline. Just to set some context, there are a bunch of MVs here, materialized views. The first materialized view is in our data warehouse or data lake, we ingest as new orders are placed. They are ingested every few minutes. And the first materialized view is basically picking up those raw order facts and then enriching them with dimensions. In this case, we join order table with customer table and nation table. And we create this enriched orders table. On top of this, once we have this enriched order table, we basically then create a few other aggregated tables, as Michael mentioned. One of that table is we basically create daily total order, total number of orders placed, total price by nation. And this data set is becoming very, very critical for our marketing team right now. They use this data set to tweak their daily or hourly spend on their online ad business. But they're not very happy at this point in time with the, and I'll tell you what the problem is. They complain that this is very slow. So let's take a quick look at last few runs of this pipeline. This pipeline runs hourly, and roughly it's taking 20 minutes. And that's not good for our business. They want to basically look at what happened in the last few minutes so they can tweak their ads spend. Let's look into what's going on here. So I go to this run. And what I noticed was that this table is actually taking 18 seconds to compute. But on top of it, there's another table, this enriched order table, which is taking roughly 11 minutes. And what I also notice is as more and more order arrives in data warehouse, this table keeps on growing, and the time to compute this is actually also increasing. Now let me take a look at what's going on here. Let me scroll down. Yeah, so what I noticed was this table, because it was a materialized view, it was getting recomputed every day, every time I was running this pipeline, so it's very slow, as you can see. Luckily, I heard Michael's talk, and I realized Enzyme is this new cool feature which can incrementalize these materialized views. So let me give it a try. It seems like it's part of serverless offering. So all I had to do is click on serverless. I didn't make any code change, nothing. And I save this setting. And let's run this pipeline. OK, so great. So pipeline has started running. There's a little bit of magic because of DLT serverless. We picked the cluster very fast. And one thing that I notice is it's getting planned. This enriched order table this time, it's getting executed as a partition override. As Michael explained, what we noticed was this order table, that order enrichment table was reading, only last few partitions were getting changed. So we detect those partitions and only recomputed those partitions. And if you look at it, I don't know whether it's visible or not. Let me increase. It just took 6 seconds to finish it. Excellent. And let's take a look at maybe this other table, which our marketing team is really interested in. So I think Michael just explained, underneath what's happening here is we actually we evaluated 4 different techniques here. So there's a complete recompute. It was available for it to run with some cost. And there's a partition override. We also could run it. But then we realized this row-based technique, which Michael explained, actually its cost was lowest. And we picked that. This is the one that basically is chosen. And we ran that. And it finished in 12 seconds. But overall, now the runtime for this is, let me see, 46 seconds. Earlier, it used to take me 20 minutes to run this pipeline. This enrich order was taking 600 seconds. Now it's taking, 6 seconds? So almost 100x improvement. Wow, that's awesome. I think my marketing team is going to be really, really happy. More importantly, my CFO is going to be happy because I'm pretty sure the TCO for this is going to be really low. And yeah, it's a mid-year review time for me, so I'm going to talk to my manager for a promotion for just clicking this serverless button. Yeah, with that, I conclude my demo and hand it back to Michael.
Cool.
Thank you.
OK. Pretty cool. And it turns out that Enzyme is actually not the only magic trick that you can use to reduce TCO in your streaming pipelines that's part of DLT serverless. So we have this other pretty cool thing in serverless where we will dynamically optimize both the compute and scheduling of your streaming queries. And so what we did here was we ran a benchmark where we were using that autoloader source that we were talking about before, and we were ingesting a huge data set. Autoloader backfills where you have terabytes to petabytes of data and you want to read them into Delta. This is often a big tuning pain for customers. How do I make it run fast enough? How do I make sure I'm spending as little money as possible? And DLT serverless does this automatically. If you look at these 2 techniques, we're comparing to a baseline of 1, how long it took. Just by tuning the admission control, how big each batch is, based on the amount of compute that was available, we were able to get a 1.7x speed up. And by adding this new and more intelligent scheduling that we call microbatch pipelining, you're able to get another 2.15. When you put them together, it's actually 2.6 times more efficient to run your streaming queries on DLT serverless. So I could give a whole talk on DLT serverless, but they told me I only had 90 minutes, so let's move on to the next part. To wrap up what we've seen so far, most use cases will actually be a mix of streaming tables and materialized views. You should pretty much always use streaming tables for ingestion. And the best practice here is to avoid complicated transformations that could have bugs or accidentally drop important data in that first initial ingest. And the reason you want to do that is because that allows you to delete that raw data. It's almost impossible to do GDPR retention over files in cloud storage, so you want to have a really short retention. Don't keep them around for more than 30 days, and you don't have to worry about it. Do all of that work inside of Delta. You can retain infinite history there. You can do all of your compliance tasks, and then use materialized views to read from that streaming table. These materialized views will automatically handle those complex joins and aggregations. They'll automatically propagate GDPR updates and deletes into all of your reports, so you don't have to worry about it. OK, so now that we've made it through the basics, I'm really excited to get to the cool stuff. Here's where we start talking about software engineering and best practices when you're doing software development specifically for data. But first, let's talk about just what is software engineering in general. In order to build these reliable data pipelines, we can learn a lot from the practice of deploying software. Pretty much all good software teams will use version control. You'll always check all of your code into something like Git. You'll use build systems. Nobody's sitting there linking their things together by hand. You have a system that understands dependencies between components. It knows how to package them. It knows how to run them in the right order. It knows how to use parallelism, and it kind of takes care of all of it for you. This could be Bazel. This could be Make. This could be Gradle, whatever. You have continuous integration. You should always be testing your code, and that testing has to happen in an isolated environment. There's no more testing in prod, no more just running DDL against your database. That's a bad idea. Continuous deployment is also really important. There should be no manual steps in how you get your data from development into production, because manual steps are where humans can make mistakes. And finally, modularization. You don't want to have one giant 4 or 5 page SQL query. Spark SQL can handle it, but it's just not very readable. You want to break it up. You want to have clear abstraction boundaries, not only within your own code, but between you and upstream teams and downstream teams. And of course, everything I've talked about here is possible to do with just plain off-the-shelf Spark, but it is a ton of boilerplate. I've seen so many Spark programs where most of the time is spent interpolating strings so that you have like the table name with the environment name concatenated together. And again, this is a distraction from what you really should be doing, which is focusing on those SQL queries. And let me give an example of why this is so important. If my code is as simple as create a replace table production report, if I hard code the destination of that data into the code, well, then when I check it out and I start doing some work on my laptop, if I make a mistake and I run it, it's just going to clobber that production database. And this is like a pretty common pattern that I see. And so this is why we created DLT pipelines. So far, we've only been talking about individual streaming tables and materialized views. Pipelines bring software best practices to a larger collection of multiple streaming tables and materialized views. A pipeline is very simple. It has 3 components. You list which notebooks or files should be read. And these notebooks and files just have DLT code. Create streaming table, create materialized view. They can be Python, they can be SQL. You can mix and match all in the same pipeline together, however you want to do it. A target. Where should this data be published to? And you will notice this is a property of the pipeline, not a property of the code. The code is independent of where the data is being published to. And then whatever other configuration you might have. Do I use serverless? What IAM role do I need? What workspace should it run on? All that kind of stuff. And DLT now automatically manages the life cycle of creating, updating, or deleting these tables. It handles the dependencies of executing them in the correct order. And it provides this isolation so that development and production can work on their own and not clobber each other, even though you're working off of the same code base. Creating a pipeline is super simple. Open a notebook, write some code in it, create a pipeline, click Start, and you're ready to go. And a key idea of pipelines is this idea of live dependencies. So if you're reading a table from outside of the pipeline, you just read it like normal. Select star from catalog, however you're going to do it. But when you're reading a table from within the pipeline, you want to make sure you're getting the right copy. If I'm in development, I want to read the development copy. If I'm in production, I want to read the production copy. And this is what the live virtual schema does. This is a virtual schema inside of Unity Catalog. And when you say live.events, what you are really saying is give me the correct copy of events for the environment that I'm running in. We figure out how to link these two things up together. And we automatically detect all of these dependencies, run them in the correct order, handle parallelism, and we also give you this nice lineage graph, which Nitin was just showing off. So let's take a look at what it looks like to do development and testing in isolation now that we have this primitive. A best practice here would be code lives in a shared repository. There are separate checkouts for each environment. So every developer should have their own checkout. Production, staging should all have their own checkout. So when you're editing code, you're not changing code out from underneath the production job. And then you create 3 different pipelines with 3 different targets. One that targets my development environment, another that targets the staging environment, and another that is the production that all of my downstream consumers are actually going to read from. And these different pipelines are what provide the isolation. So what's going to happen now, to kind of go back to that example we just did, when I make a change, it's happening in my development environment. And only after I make that change correct and I validate it in continuous integration am I going to push it up to production, where it will be automatically deployed into production with no manual steps. This works even when you're publishing into multiple schemas inside of the same database. So this is a feature that just went into preview that I'm really excited about, because tons of people have been asking for it. Let's say I have a pipeline, and I want to publish both to the marketing schema and to the report schema. Well, now we need to make sure that there are isolated copies of those schemas as well. So what you'll notice is I just say marketing and reports, and then I say live.marketing, .table. And what it's going to do is it's actually going to concatenate these things together. So it will create a schema called marketing dev and reports dev and marketing prod and reports prod. All this interpolation is done automatically, and it will automatically link all of these related copies together for you. So now even for these complex pipelines that publish to multiple places, you can handle all of this isolation. Now that we've got pipelines, you might be saying to yourself, well, how big should a pipeline be? Should it have 1 table, 10 tables? And there's really no correct answer. This is up to you and your business requirements. But let me give you some high-level guidelines. A larger pipeline is going to give you better TCO, because it turns out more things happening always allow us to multiplex that cluster more efficiently. When one node is idle, there's another query that can use that stuff right away. So in general, bin packing things into smaller numbers of pipelines is better. But at some point, you're going to start to hit scalability limits within the driver. Tens of streams, hundreds of streams. It really depends a lot on the volume of data, how many columns you have, how complicated your transformations are. It's something you're going to have to kind of experiment with and measure. But there are some good places where you probably want to create separate pipelines. If you have 2 different teams who have different deployment schedules, well, they should probably have their own pipeline so they can deploy on their own. If you have application-specific boundaries, like between training and serving, you might want to create different pipelines there so you can update those things independently. But in general, larger pipelines will just give you less orchestration, less things to worry about, and better resource utilization. Another trick is modularizing your code. This is I'm not going to spend too much time on this because it's basically how you do it in SQL as well. But you can create views inside of DLT. And these views, the right way to think of them is just like in SQL. It's just a name that is substituted with a query. So instead of having a 10-page SQL query, you can have many views that then get queried together. And this breaking it up not only makes your code more readable, but because of expectations, you get this really nice superpower. You can now assert conditions about those intermediate results. You can make sure the input to that join has these conditions, and that's pretty powerful. But the thing you have to be aware of is views, just like outside of DLT, are recomputed every single time you query them. So if you are reading the same query 4 or 5 times, you're recomputing that thing 4 or 5 times, it might be more efficient to create a streaming table or materialized view, because then it will get computed once, and everybody can share those results. Another really cool trick of DLT pipelines is they completely take care of lifecycle management. And I want to again clarify, this is UC only. If you're using Hive Metastore still, you have to do these steps manually. But in Unity Catalog, you need no migration scripts for your DLT pipelines. When would you need a migration script? Well, let's say I remove a table from my pipeline. In a traditional database, you'd have to use Flyway or one of these other systems that would go and say, yes, this table was deleted, so now I'm going to delete it. You'd have to make sure that it handles the cases where the table's not there. It ends up being pretty complicated. DLT is a fully declarative spec of what should exist in your data lake. And so if you delete a table from the pipeline code, we will remove that table from Unity Catalog. If you don't want to delete it, do not remove it. If you remove a table property, we remove it. If you change the partitioning of the table, we make sure that partitioning is correct. The right mental model for DLT is as this system that is constantly comparing your code and the state of the lakehouse and making sure that they are in sync to each other. And anytime it notices something is out of sync, it will change that. Now, you might say that sounds really scary. What happens when I push something to production and I just accidentally deleted a table? Well, never fear. All of the deletes are lazy. We log exactly what's happening. And if you recreate that table, you just revert that git commit and put that back into your code, we'll pick up right from where we left off with no data loss. And all of this is recorded in the event log as well. So you can set up continuous integration scripts that tell you a table was removed. And this is much more powerful, because if you think about what would happen in a traditional system if you accidentally deleted part of your source code, that table would just go stale. And you wouldn't even know that it wasn't getting updated anymore until one of your users complained to you about the results being wrong. So this makes it much safer to ensure that you're always doing the right stuff in production. I talked a little bit about Python, but I want to deep dive just a little bit more. So as I said before, all you need to use are our Python API. You can use all of the stuff we've been talking about in DLT so far. I just use SQL so far because it's easier to put on slides. But all you do is create a function, annotate it with DLT table, and return a data frame. And we will create that table for you. You can control all of the options by passing different arguments to that decorator. You can use UDFs and pandas UDFs and all the different things. You can use PySpark. You can use koalas. You can even use strings of SQL that you interpolate in Python, whatever works best for you. And like I said before, you can mix and match SQL and Python all in the same pipeline, so you can use the best tool. So I often use SQL for all of my reports, but I use Python for my data engineering, but whatever you're most comfortable with. You can use all of the libraries with pip, so if you want different functions that you're going to use inside of your UDFs, you can use pip install. You just put this in any of your DLT pipeline code. And there's one important thing to understand here. Because all of the tables are stitched together into one single data flow graph, you are running in one library environment. So in your pipeline, you can only have one version of each Python library. So if you install a Python library in one notebook, it is available globally to all of the other notebooks in that pipeline. And this is pretty much fundamentally required because views can reference UDFs and views can be included in other tables. So it has to be done that way. If you need to use separate versions of libraries, use different pipelines. And here's where Python gets really cool: metaprogramming. A pretty common pattern that I hear over and over and over again is I don't need to ingest just one table. I need to ingest 1,000 tables. And it's very tedious to write out the same create table statement over and over and over again, changing only a tiny part of it. Metaprogramming allows you to do this using control flow inside of Python. So in this example, I have an array that has a whole bunch of different regions. I need to create the same sales report for every region. And so all I do is say, for each R in region, call this function, and then I create a different DLT table for each region. You'll notice something interesting about this code, that DLT table annotation is in its own function, and this is critical because of how Python does variable capture. When you have a Python variable and it's captured by a Lambda function, and we run that Lambda function later, it's going to have the final value of that loop. So if you were to put all of this in that loop, what's going to happen, and this is super confusing, but it's how Python works, you will end up with 10 tables with exactly the same arguments because all of those functions are evaluated at the end of the loop, lazily after it is completed. By creating this extra function here, you are capturing the values at that moment of loop iteration and using those consistently. So if you didn't understand that, that's OK. Just copy this code. Do it this way. Another trick here is parameterizing DLT code. Metaprogramming isn't only for Python users. SQL users can do it too. And all you have to do is use this $ notation, and you can substitute in different things into your SQL code or into your Python code. And you can do this for a variety of reasons: to improve code readability or maintainability, or to reuse the same notebook in multiple different pipelines, but with different input parameters. But remember, this is not an imperative system. This is a question, again, that I get over and over and over again. How do I tell DLT which date to process? You are not telling DLT what to do. If you were to say, for example, update only this date, you are not saying insert overwrite this partition. You are saying only this partition should exist, and we will delete all of the other partitions. So don't fall into this trap. If you want to do stuff incrementally, use streaming or Enzyme, and let us figure out what data is new. And if you have to insert overwrite partition, that is totally valid. You should use workflows in DBR for that. That is how you write imperative code inside of Databricks. But a great way to use this is actually a valid way to use it, is for configurable data volumes. So let's say I want to make it configurable. Am I going to have 1 year's worth of data, 3 years worth of data, 10 years worth of data? That's a great thing to parameterize, because you are actually saying, I want this complete data set. You're not picking how it's done. You're saying what should be done. OK, almost done. So all of this seems pretty complicated. Creating all these different checkouts, creating all these different pipelines, making sure that all of these pipelines are in sync with each other, that's a ton of manual work. And I started off this section of the talk by saying no manual steps. And that is why we have created this pretty cool new thing, which is my third announcement, Databricks Asset Bundles. And the idea here is, instead of having this onerous, error-prone process where you create these things manually, DABs, or DABs, allow you to version control everything, not only your code, but also the jobs, notebooks, clusters, pipelines that exist inside of your Databricks workspace. If you're familiar with Terraform, this is actually built on top of Terraform. It's a simpler version of Terraform specifically for Databricks. And the really cool thing about this is now we can automate the creation of all of these separate isolated environments. So a real quick description, although I'm going to go through this fairly quickly. There is documentation online, and I'll provide a link to get to it at the end. But the basic way that DABs work is everything is in version control alongside those notebooks. We specify a resources section, which says which resources should exist. In this example, I'm creating a pipeline called my pipeline. It automatically is interpolating which environment it's running in. And then I have two different environments where I override properties of that pipeline. In development, I'm publishing to the dev schema. In production, I'm publishing to the production schema. And it takes care of all of this overriding and interpolation. Now, there's a pattern you want to use here to make your DLT pipelines work well, which is you want to structure your pipelines correctly by separating sources and transformations. Sources are queries that read from external inputs. This is where I was talking about modularization. You want to have interface boundaries between you and your upstream consumers. So ideally, these sources have little to no transformation, and you can use views. This is a great use case for views because they have no extra cost inside of the pipeline. Transformations, on the other hand, are where the real work of your pipeline is done. These are the same in all environments. And then the other best practice here is use expectations for validation. Unit tests are great, but they're not going to protect you from the upstream team changing the data type and not telling you about it. So expectations are a much more robust way to ensure that your pipeline is working not only in development, but also in production. Let me give a concrete example. So let's say I have a pipeline and I have some sources. I'm reading from this upstream table called prod sales. In production, I'm just going to read the table. It's super simple. Just select star. In development, however, I don't want to read that whole table. That'll take way too long for every iteration. So instead, I'm only going to read the last day of data. But the transformation doesn't have to know which version it's querying. It queries from live.sales and gets either the complete table or the small subset of the table automatically. And there's a whole bunch of cool ways you can create test data inside of DLT to speed up development and testing. You can use this subset trick where you just filter out a time period. You can read hard-coded examples from JSON if there's like specific pathological inputs you want to deal with. You don't even have to create JSON. You can actually just hard-code those values into a SQL view. So in this example, I have kind of two pathological examples. Do I handle the negative profit case? Do I handle the very large profit case? Do the right things happen? Or if you want to kind of test the scale of your pipeline, you can randomly generate data using Python. And so now putting it all together, when I create my pipeline, I have all of the transformations up there in the resources section. I have all of the sources down in the environment override section. And now my development is super fast, and my production is correct. And so with that, I would like to bring up Dylan, who's going to show us how it all works. Okay.
Hi, everyone. I'm Dylan Bostwick. In the real world, I am a solutions architect at Databricks, and I like to spend a lot of time helping folks in the field with Delta Live tables. But for now, while I'm on stage, I'm going to pretend I am one of you. I'm basically a data engineer who is working on a pipeline, right? So this is actually a loan pipeline, right? So we're trying to approve loans, and I'm working for a bank. And there's a change that I need to make, right? I'm actually working on all of this in VS Code, and I added this line here, DLT expect or fail. This is basically saying that I want all of my loans to be newer than 2014. And if not, I want the entire pipeline to fail. The first thing I'm going to do is check this into Git. You can see that changed. And let me go ahead and push that to the branch. We can see I'm currently working on a separate branch, right? So even though we're working with data, we're working with a lot of different objects like pipelines and all these different things, I'm actually using kind of traditional DevOps and software best practices. So I'm using Git flow, I've checked out the separate branch, and I'm actually working using the VS Code extension for Databricks to run all of this in my development environment, right? So you can see on the left-hand side, like Michael was alluding to, I actually have multiple different Python files that I'm using, and perhaps I might have some SQL files or something like that as well, but this is basically how I'm building the loan expectation pipeline in development. So the next thing I'm going to do, like a good software engineer, is I'm going to go into GitHub, and I'm going to create a new pull request for the change that I made. All right? You can see this is the branch that I checked out. And you can see that change that I made there. So we're actually very busy at the bank that I work at. We don't really have the resources or the time to manually do all of the unit tests and integration tests and then deploy all of those changes into production. But there's a lot of regulatory requirements where we need to be able to test any change that we make to the pipeline across data that's sitting in staging before we push it into production. So what we're going to do is look at the last decade of DevOps best practices, and we're going to do this thing called CI/CD, right? CI is when we're going to do, integrate and test all of the data automatically, and then of course the CD is when we're actually going to be deploying that into the production workspace. So when I actually submit the pull request, I'm using GitHub Actions here, and all of the every single push that I'm making is going to actually run some automated CI checks. There's actually two here. One succeeded and the other failed. And if you look at it, the first one is where we do this thing called deploy bundle, and the second thing is where we're actually doing the run pipeline update. So it looks like we were able to deploy it, but it wasn't actually able to run. And when we go to look at the files changed, you can actually see in the GitHub Actions script, we have it set up so that in line, you can see a big X on that expectation. So what actually happened here? We ran an end-to-end test on staging, and the change that I made actually failed based on the real data, and as the developer, I can pretty easily see where the issue was. All right? Going back here, if we actually open up that action, you can see the deploy bundle succeeded. These are all the different things. We could ignore a lot of the setup for now, but we can actually open up, this is the part that I really care about. This is actually running on the GitHub Actions box. I run this command called Databricks bundle deploy, okay? That's actually part of the Databricks CLI. And what you'll also notice is I'm passing this thing called a Databricks bundle environment, right? And it just so happens I want that to be the QA variable. And what that's going to do is it's going to tell the Databricks bundle to run the QA version of this deployment. So the deployment actually succeeded, but the problem was with the run. So it looks like there was something in the QA, or what we call the staging environment, where it actually failed when it ran, even though the pipeline was able to deploy successfully. Okay? So I'm going to go here. I talked to my manager. My manager said, actually, it was 2012, not 2014. We got the date wrong. My bad. So I'm going to quickly make that change. And then I'm going to push that again. So what's actually happening? What is this bundle thing? Let me hop over to another file that is actually located in the same directory next to all of the actual code that's implementing the pipeline. This is our bundle YAML file, And it specifies all of the different workspace objects in this modular, extensible way, where everything has a sort of single responsibility, right? If you've worked with infrastructure as code or you have any background in DevOps, this looks pretty familiar to you, right? What we're doing is all of the different infrastructure, not just the code itself, we're defining in the code, so it's a lot easier to manage, okay? It's kind of like Terraform, but for Databricks objects, right? So we have a name for it, and if you scroll down, we have this thing called resources, and we're actually creating this thing called the loan approval pipeline. And what you'll immediately notice is the name we're giving it, we're going to interpolate that bundle environment variable, right? So when we're running this in the QA environment, it's going to say QA loan approval pipeline, but we can also do the same for development and production, right? So we can do things like interpolation. Up here, these are the things that are going to be shared across the different environments. But if you scroll down, we're going to do this thing called substitution, where now we're going to define environments, and we're going to start to sort of mix in different properties, right? So this is going to make it a lot easier for us, number one, as a team, to see how all the different configuration changes between the environment. But more importantly, it's a lot easier to make those changes when we're going from development to staging to production with a lot less friction. So here you can see we're actually doing different workspaces. Right? So we're actually going to be running in different environments with different data, sitting in different cloud accounts, things like that. And for example, development and QA are both going to have development mode turned on. That's, of course, the DLT setting for development mode, which makes it easier to do cluster reuse. And if you scroll down to production, we're going to make a couple different changes. Right? For example, we're going to say we always want to run Photon in production. We're going to turn off development mode, right? So in the past, you would actually have to go into the UI, click the button, and there wasn't really an automated CI/CD kind of best practice way to do that. We can be more opinionated about the kind of infrastructure that we want Delta Live Tables to manage for us, and we can even specify other kind of Databricks parameters like permissions, and of course, in the production environment, we're going to lock it down, so we're going to use Databricks ACLs as well, okay? Jumping back over to GitHub again, let's go back to the pull request. It looks like 2012 actually worked. And now, both the checks have passed, and we can go ahead and merge the pull request. All right, now we're merged. This is going to kick off another Databricks bundle deploy into production, and we're finished. I think everyone can appreciate the green check mark. It's a nice dopamine hit for all of our engineers. Makes it a lot easier. Thanks. Yeah.
OK, so if you thought that was pretty cool, you should definitely check out bundles. There's actually a session, I believe it's after this, where they're going to be talking about it in more detail. This is actually a new feature of the new Databricks CLI that I think we're actually just previewing as part of this summit. There's a link to the documentation. You can contact this email address if you want to learn more. And with that, I encourage you to try building your next data pipeline with DLT. Thank you so much.